Good afternoon, everyone. So today I will share with my experience on the analog IC design awareness programs. And before we conduct the offline season, so can I share my screen right now?
Yes, anytime, all yours.
Uh, okay, thanks. Yeah. So anyone can see this slide, right?
Yes, we can see your slide.
Okay. So thanks. So I will begin. Yeah. So good afternoon, everyone. Before we begin the technical part, so let us take a few minutes to warm up. When people talk about integrated circuit today, they often talk first about the microprocessor, right? And AI chip or memory and digital system. So I believe all of you have recognized today the AI chip and memory. They become already very expensive, and the price are very crazy right now. So that is understandable because the digital chip are easy to describe. They are more computing power, more data, more algorithms. But if we look carefully at this real electronic product, we will notice something very simple. The real world is not just digital, right? For example, our sound, voice is continuous, and also light is also continuous, and other factors such as temperature, pressure, motion, radio wave, I mean the high frequency wave, um, power supply noise, or even battery voltage and sensor signal, they are all continuous. So digital chip can calculate, but it cannot directly touch those physical signal without analog circuit helping it. So today we are not here to say that the analog is more important than digital, or that the digital is more important than analog. Actually, a modern system need both circuit. Yeah. The digital part gives our intelligence, storage, communication protocol, and also control. But instead, the analog parts give us the system eyes, ear, power, timing, and physical connection to the outside world. For example, for the product like our handphone, the eyes are what? Are just the RF receiver. So how about the timing? The timing is actually the clock. So that's all. Sorry. Yeah. In AI infrastructure, analog circuit appear in power delivery, high-speed interference, and also interface, clocking, sensing, and thermal management. So in electrical vehicles, analog circuit appear uh, in battery management, radar, lidar, motor control, power conversion, and safety sensor. Yeah, I believe all of you already recognize this field because these are hot topic when you searching for a job in the industry. Yeah. So in phones and wireless device, analog and RF circuit. RF means the radio frequency. Yeah, it's a high frequency circuit. I think all of you have learned this course in undergraduate course. Yeah, but maybe you are new to RF integrated circuit. Yeah. This RF circuit decide whether the system can receive weak signal and transmit clean signal. Yeah. In industry equipment, analog front end decide whether tiny sensor signal can be measured reliable in a noisy environment. Yeah. So for students who are just entering this field, analog IC design may sound a little bit difficult for you. And honestly, it's not a subject that we can master by just listening to one lecture. But the purpose of this program is somewhat different. And we actually want to pave a new way. We wish to build a first mental map and understand what analog IC designer care about, why they use different certain concept again, and how the beginner can move from classroom theory to practical design ability. So please do not worry if every formula is not clear today. Try to follow the story and signal, yeah, especially weak signal and performance metrics, their trade-off, circuit block, verification and application. Yeah, at the end of this course, we will have a practical design uh, uh, season for each student here, and we will conduct some simulation and experiment on a real circuit. Yeah. So if you can build that story in your mind, you will already have made a very good start. So with that if motivation in mind, so please let's now organize this whole program so we know where we are going and how each part connect to the next one. Yeah. Okay, so let's begin our course today. So the first slide here, I will like to show the course flow. Yeah. So this program is arranged like a guide walk rather than a list of isolated lecture. Yeah. I believe in university is more likely to be a list of isolated lecture, right? So you learn each circuit individually, and sometimes you cannot connect the knowledge between them. So uh, so what is the problem here? So the problem is we cannot understand their limit and their trade-off. Yeah. So for example, how about the gain and the bandwidth? So this actually have a trade-off, but we cannot sometimes cannot link them together. So we just calculate gain and we started, then calculate bandwidth, we started. We cannot understand. So why these two parameter are connect, right? Okay, so here the main purpose is to walk through the learning journey from overview and pre-requested to a fundamental concept, circuit block, application, carrier, and Q&A. So a practical way to read here is to look for the design question. So behind the diagram, the question here is only what is the definition, but sorry, the question is not only what is the definition, but also what decision does this help me make as a good designer. So this is the program is divided into overview. So this is an overview here, and the pre-request course, analog fundamentals, circuit block application, learning paths, and Q&A. So I think all of you care about more on the application because this will actually help you to seek a job after you graduate from the university. Yeah. A useful way to explain the topic is connect it with one small design example. So ask what the input is, so what the output should be. So this is actually the input-output characteristic, right? So what metric matter most and what could go wrong if circuit is used in a real chip? That question-based style key the lecture and I think it will prevent the discourse from becoming a list of isolated definition. Yeah. So for beginner, I suggest taking one simple rule from the topic. If the rule is clear, the detailed equation can be added later. So we can listen first for the logic, then return later to formulate the circuit detail. In analog design, knowledge became useful when we can connect a number on a waveform, a transistor in a schematic, and requirement in a system specification. Yeah. Okay, so let's talk about the cost matrix. Yeah. Okay. So this terminology, cost matrix, is a very useful word in the lecture in China. So the cost matrix in China means how this cost can connect to other costs and how this knowledge can be merged together to make this course better to be understood by a student. Yeah. A metric is useful because analog IC designers never learn from only one course. So here the main purpose is to connect pre-request course, core analog concept, practical skill, and learning output in one integrated matrix. So a practical way to read here is to look for the design question behind the diagram. So we should also show the diagram here. So it's a little bit busy here. Yeah. So first we need to learn circuit analyze in I think in the second year of no, sorry, I think it's the first year course, right? And then we study the semiconductor device in the second year. Actually, in China, is I think it's a semiconductor physics, right? Yeah, we study the basic fundamental physics of the diode and the transistor. And then later we study the signal system, particularly the large signal response as of a linear system, right? And then before we graduate, we have to study the EDA tools awareness. Here, EDA means the electronic design automation. I think all of you already know what is that. So it actually is a software, right? Like Virtuoso or ADS, we can use to simulate the circuit. Okay, so a practical way to here is to look for the design question behind the diagram. The question is not only, sorry. So a useful way here to explain is to connect one small design example here. So here we have the input, and then we have the response of the signal, sorry, of the system, and then we can get the output. Yeah. Okay. So next we talk about the skill. What skill we have to build after this course. So we usually want to know what we can actually do after spending time on the course. So here the main purpose I would like to show you is the ability we can gain, including specification. I mean the specification of the circuit, right? So for open, we have already start. So what is the spec? It's normally gain, right? The small signal gain and the input output impedance and the bandwidth. And so these are the spec and their performance metrics. So why we need to talk about metric? Because these parameters are not isolated; they are connected together. Yeah, we have relationship to describe. Yeah, their I mean their the linkage, right? For example, we have a higher gain. Probably we have higher gain of the amplifier, so we have to sacrifice something in return. So normally we show properly consume more power, or we have to sacrifice the bandwidth, right? So this is the performance matrix. And then we also have a small circuit model, simulation, behavior, waveform interpretation, and also later we have to document documentation, right? So a practical here is to look for the design question behind this program, this diagram. So we have understand metrics. So what is the important metric? And then we have to analyze the circuit. Yeah. So this is for example, is a differential circuit. So what is the pros and cons of this circuit? So why the input output impedance vary with rest frequency, and then we have to simulate their behavior using our EDA tool, right? And then we can get the input output waveform. For example, we input a small signal, rather big signal in a micro maybe millivolts of the signal is they are very small, but we can get a amplified signal at the output is at a range of few volts, right? But why we cannot get higher? So we have to think about why we can't go higher. Yeah, maybe it's already linearized. I mean, it's transistor already linearized, or maybe it's limited by the power supply. Yeah, that's all we should consider in our course. Okay, next we talk about our employment direction and career pathway. Uh, so I think all of you care about more on the career than just one course. Yeah. So for many students, so motivation becomes stronger when the technical content is connected to future choice. So here the main purpose is to relate analog IC learning to employment directions such as analog design, mixed signal design. So what is that? What is mixed signal design? Sometimes emerge digital, analog, and also high frequency design into one chip. So it's sometimes referred to SoC, right? So silicon on chip, yeah. And also the RF power management, layout verification, and also application engineering. Yeah. A, a practical way here is to look for design behind all this I have shown you. So career direction include design, layout, verification. So I have named this before. Yeah. So I think most of you just for undergraduate student going to a design house is somewhat difficult than a graduate student. Yeah, because we don't have sufficient knowledge to design circuit. I mean a robust circuit in a short time, right? So in China, actually, most of the students go to the fab. I mean the semiconductor factory. Yeah. Sorry, semiconductor fab. Yeah, after they graduate from school, but not going to the design house. So many students here and in China pursue the graduate course and taking 3 or 5 years to get a master or PhD degree before they can really go into the design house. Yeah. So it's a long journey to study this course actually. Yeah, actually spend more than 5 years to study the analog in this gray circuit. Yeah. I think even in most of the Asian country, so the basic requirement for employee is about at least 5 years, and sometimes 10 years experience. Yeah. Okay. So career preparation is not only about knowing many concepts. Yeah. It is about showing that you can think like an engineer. Can you read can you read and understand a specification? And can you design a small circuit block, or can you explain a trade-off? Okay, I think in the interview, yeah, the expert will ask you many trade-off, which is the performance metric among circuit block. Yeah, you must act quickly and answer. Yeah, this trade-off. So can you debug a failure simulation, or and also can you write a clear report? So this ability matter in interviews and research and project collaboration. So I think for beginners, I suggest taking one simple rule from this topic. So if the rule is clear, the detailed equation can be added later. Each direction use analog thinking in a slightly different way. In analog IC design, knowledge became useful when we can connect a number on a waveform, transistor in a schematic and a requirement in a system specification. Okay, so now this idea is in place, we can continue naturally to course relevance. So where this program fits and where the thinking became more specific. Okay, next we talk about the course relevance. So where this program fits. So analog IC sits between base theory and real chips. So it naturally pulls knowledge from many directions. So here, I just wish to show you how circuit theory, device physics, signal processing, EDA verification, and system applications support analog IC design. Yeah. So when a student review earlier course, they should not ask only whether they remember every theorem. A better question is whether they can reuse idea in a circuit. So for example, in the first year, we already learned the Kirchhoff laws, right? So in the basic circuit course. So actually the Kirchhoff laws help us to set the operating point, which is the static point for each transistor. So semiconductor physics help us understand device behavior. Yeah. So we studied semiconductor physics in second and third year. Yeah. I think for most of the students, these physics courses are more difficult than circuit course, right? Okay. So signal processing, so which we take in the third year. And signal processing helps us understand bandwidth and noise. Programming and tools help us simulate, organize data, and verify design choice. Yeah. So actually, programming is become more and more important right now because we have the AI, right? We have the tools already embedding the AI. So programming actually gives the our power, yeah, to automatically get the optimal operating region for each small circuit. Yeah. For large scale circuit, I'm not so sure, but for small circuit, actually already many people show that we do not need to calculate or we do not need to simulate the circuit at all. The AI can help us understand or even get the optimal sizing for each design. But even of this, we still have to understand why AI can get such optimal region for us. At least we should understand basic fundamental of this circuit. So how it can operate. So what is the limiting factor of this circuit? And so what can we achieve by just small circuit, right? So for beginners, I suggest taking one simple rule from the topic. If the rule is clear, the detailed equation can be added later, right? Okay, so this is the thing. I just Okay, next we can talk about recent industry signal and our opportunity. So modern electronic look digital on the surface, but every real product still has to sense power, communicate, and control something physical. So here, I wish to show you. So for example, we can use AI infrastructure, vehicle, industrial automation, communication, and power electronics as a soft opening for why students show care. So for example, right? For example, here, AI data center. So an AI server may be judged by computing performance, but its reliability still depends on voltage regulation, current delivery, temperature sensing, clock quality, and high-speed signal integrity. So all of these are sub-area of the analog circuit design, and part of it are already the RF design, right? Because they are related to very high frequency response of the system. A small vehicle may be advertised by intelligence and software, but radar, battery monitoring, motor control, and safety sensors all rely on analog circuit. That's why analog knowledge stays useful even when products name challenge. Okay. So next we talk about industry trends. So why analog IC skills are still important, right? Okay, for example, for the each AI and IoT, so why is this is major? Why this is matter? Because AI. So at the beginning we have talked about AI, right? It's actually a digital intensive circuit. Yeah. So why we still have to AI? Why we have to study the analog circuit? Yeah, because we still need to have the interface circuit before all AI chip, right? For example, between the microprocessor and the memory. So we need this interface circuit to transmit and receive data, and we have to synchronize them. So that's why this area is more likely to relate to the analog circuit design. Okay, so how about IoT? So it's actually an Internet of Thing. So Internet of Thing circuit also is a complex circuit. It's also a SoC. But why does it matter when we're talking about analog circuit? Yeah, because it's actually a very low power circuit. Yeah, extremely low power circuit. So we have to study under such low power consumption. How can we design an interface circuit and the transceiver circuit and also the synchronized clock in such a SoC? So these are all analog circuit, not just the digital circuit. Yeah, of course, we have to synchronize all of this circuit into one a single chip. So we still need some something like background calibration, yeah, in the circuit, yeah. So I think at the end of this course, some student will have chance to learn how to design a background calibration. It's actually a temperature sensor, yeah. So why this matter? Because the performance of this chip vary with the temperature. We have to calibrate their performance when the temperature varies. Okay, the next one is the RF and connectivity. So how it is related to the analog circuit. So as we know, the when we talk about the gain in uh in analog circuit, we normally relate to a low frequency response of the circuit, right? So actually we talk more about the near DC gain when we design a small signal amplifier. However, in the radio frequency or even higher frequency like millimeter wave, since the frequency is already very high, so the transistor gain response will drop significantly. So that's why we cannot get a real high gain at such a high frequency. So the connectivity have will have a problem. Uh, Here the problem is likely to be a error, right? To be a transmission error. So here we have to study when the operating frequency increase too high, how can we even design amplifier to have sufficient gain to ensure the correct connectivity between device. So at this stage, a single stage amplifier is I believe is insufficient. And we have to design a multi-stage and also uh, more likely to be a multiple branch amplifier to improve the gain of one amplifier. So the circuit become rather complex at this stage. So this is actually very challenging for the analog designer. Okay, the last one is the power and energy. Yeah, so it's more likely to be a low dropout circuit, right? LDO, and also the DC-DC converter. We actually talk about how we can convert high voltage to a small voltage. For example, in China, the voltage we can see is 220 volt, right? But we cannot use this voltage directly when we charging our, for example, charging our device. We must have some converter between them. So the DC-DC is actually the voltage conversion between uh the 220 volts to something like a 1 volt or even lower. Yeah. So here we must face a problem, the conversion efficiency or the conversion loss. So our target is to first we have to ensure the functionality is correct, right? The conversion, and then we have to reduce the conversion loss of this circuit to ensure the high energy efficiency for the system. Okay, so actually we have a lot of topic to discuss for this analog course, and we will go through all of them in our course. Yeah, before each of you can go to the industry. Yeah. Okay, so we'll discuss about what we concern as a beginner. So what will student usually ask? Okay, so most beginner do not lack talent actually. So we simply do not yet know which part of the subject to hold first. So here, the main purpose I would like to share is address common ancestry about mathematics, device physics, simulation difficulty, and how to begin learning without fear. Okay, so first we still have to gain sufficient confidence when we study this course. Yeah, because we already close to the graduation, right? Which means we have already studied fundamental circuit theory and semiconductor physics and digital analog circuit and signal processing. So the problem here is how can we connect or synchronize this knowledge together? For example, how can we use other course knowledge to solve the knowledge here in analog circuit design? Yeah. So, for example, uh, I think some of you may fear about math, right? Because sometimes they are too complex. Actually, in analog circuit design, we don't need to solve very complex maths. We just need to use simpler equation to describe the behavior of the circuit. Yeah, we do not wish to make the equation very hard to understand, but instead we wish to make the equation understand by all of the people actually. So we want to keep the equation compact. Yeah, so it's actually an engineering problem. Yeah. So math itself is complex, I believe. So, but in engineering, we try to make it compact. Yeah, make it compact and understandable, easy understand. Yeah. So next we have to study the physics device. So why? Uh, it's not like a digital circuit. We just need to learn a lot of the programming skill. But here we have to study the physical device. Sometimes we have to understand why the circuit has its limit. Yeah. For example, if the gain is not large enough, so what is the quickest way to increase the gain? Uh, I think many students will know we can just increase the power, right? We can increase the power consumption of this chip and make this chip to burn more power. So how can we increase power consumption? Yeah, a practical way, I think some of you will know is to just directly increase the power supply. So without understanding of the device physics, we uh we assume the voltage can be increased as large as possible until we can get the desired gain. Yeah, but if we have studied this course, we know the transistor will have the breakdown issue. Yeah, there is some breakdown can be reverted, but some of them cannot. So it's a permanent effect to destroy the transistor. So we still have to learn some device physics to know the limit of the transistor and how it can respond to small and large signal. Yeah. So also we have to know the operating point of the transistor, right? Is it in saturation, linear, or even cutoff region? Yeah. Some circuit because the signal is large enough, some circuit actually will make the transistor operate in different region over time. So the analysis become more difficult than a small signal analysis. So at this stage, we still have to uh, understand the device physics. So what is the limit? How it can respond to a small or large signal? And particularly for RF design engineer, we have to understand why the gain drops over the frequency and how to compensate this drop by our circuit design. Yeah. Okay. So next, will simulation replace understanding? Yeah, I think in many textbook, also in some forum, so people would say maybe people would say I'm a spice monkey. So what does that mean? What does that mean? So what is spice monkey? Uh, I believe spice monkey refer to people who rely on simulation only to to simulate a real circuit without deep understanding on the circuit itself. It means that just a tuning. It's a tuning process, right? It's a tuning process without understanding the circuit. So, students normally uh, are spice monkey because sometimes we are not very confident about the circuit. We do not know the circuit limit and how the circuit can, what performance the circuit can achieve. And we just rely on simulation to tune the parameter, right? To tune the, for example, the sizing, the size of each transistor, and see the result every time. So this is Spice Monkey. Okay. Sometimes for small circuit, I think this will help because circuit the complexity is too low, and sometimes we can take even few hours to simulate something that have a good performance, right? I have to say this is for beginner. Yeah, this is reasonable for beginner, but not practical for engineer. Yeah, because in a real case, circuit is not just as simple as you know. Yeah, even in our lecture, and I think it's a Razari book, right? Some circuit have more than 10 transistor uh, to tune. So a few hours tuning is not sufficient to get a good result. Sometimes the circuit even fall into undesired operating range. For example, the amplifier, if you have feedback, so tuning the gain will by EDA will help. Yeah, we can get a higher gain by tuning some parameter, but unfortunately, the circuit will automatically fall into some region like oscillation. Okay, so this will actually destroy the whole circuit because analog amplifier cannot oscillate, right? Okay, so it means we still have to understand the circuit before we conduct simulation. We must understand what is the limit of the circuit, and what is the, for example, what is the maximum gain we can achieve by just simulating this circuit. We cannot go beyond that. Once we go beyond that, either simulation is not correct or either the circuit fall into other region that can impede the correct operation of the circuit. So understanding the fundamental of the circuit is still quite useful. Yeah, then just only do simulation. Uh, Okay, the last one then we should ask, is the second analog circuit difficult? Okay, I have to say it's actually difficult. Yeah. Because this is not just one isolate course actually. We have to combine many knowledge from other courses before we can start this course. For example, the basic mathematics, device physics, and also some ability in the EDA tool, right? So actually, this course is difficult because it actually integrate multiple uh, skills into one course. Yeah. Because we have so many trade-off and also performance metric in this course. For example, the trade-off between speed, power, and area. Okay, when we talk about area, we actually talk about the layout, right? So in this course, we do not study layout, but I think most of you already know this is also important when you go to industry, because the interview will ask the same question. Okay, so I believe this course is difficult, but I think we can tackle them. So how can we tackle them? So we have to gain a solid foundation on the device physics and also the signal processing and also the EDA tool before we study this course. Yeah, when we study this course, we must think. So if we cannot get answer from this course only, can we get answer from other course, right? So for example, why the voltage cannot go higher is it is because of breakdown. Yeah. So why can we get reasonable performance in the EDA tool? Because the operating point is not correct. So something like that. Yeah. Okay. So next we talk about the student decision. So what decision can we have? Uh, for undergraduate student, actually, in China, so we do not, frankly speaking, we do not actually have much choice here because the because a minimum requirement is a master or PhD student for a design house. So many undergraduate students can only go to the how to say it's a semiconductor fact. It's actually it's an industry. It's an industry to so what is the nature of the the job? The job is I think most of the job is to for example to go to the how to say it's a manufacturing, sorry, it's a manufacturing flow. Yeah, so most of students can go to side for example uh to, to study to learn to study the usage of some manufacturing equipment. Yeah, or to collect data from the force testing, something like that. It's not really a analog circuit design. Yeah. So actually, I believe in the future, so more and more students have to pursue the master or PhD degree before they can real go into the design house. Yeah. So what can we choose after this program? Assuming we have maybe have a higher degree. So the first one, yeah, the first one is which is also a very high salary type, job is an analog mixed signal design. So we design something like amplifier, actually open, right? Open and reference. So with reference is a high precision reference for the for example the mirror, right? The current mirror or some the the temperature sensor, right? And also ADC and DAC voice data, analog to digital converter and digital to analog converter. So these circuits are very hard to design. Yeah. And also we have to understand each specification before we go to the interview. Yeah. During the interview, the expert will ask many yeah specs. Yeah. For example, during your master or PhD studies, so what spec have you got? For example, for amplifier, what is the near DC gain? How about the gain bandwidth trail? How can you extend? How can you extend this limit? And for example, for the reference, so how accuracy of the current mirror, and how about the temperature can vary the accuracy of the reference. For ADC and DAC, so they are too many to discuss. Yeah. So for example, the noise and the quantization error, and also the how many stage you are using for example for the pipeline, and also what topology, for example, delta sigma or something like that. So what topology you prefer for a specific application. Yeah. So you have to answer quickly. So what is the trade-off between each for each topology, for example, for the flash ADC, it's preferred when the speed is your concern, right? However, the quantization error is large and is also very power and area consuming, right? So how can you improve it? So you can say you desire you have other choice like pipeline pipeline structure and also oversampling structure, and you have to spec. So what is the proof and con of all this topology, and why do you think some topology is quite suitable for the for some real scenario the expert give you, right? Okay, so the next one is the RFIC. So this is radio frequency IC and the community circuit. The first one is LNA, so what is that is also is actually a low noise amplifier. So what is the difference between LNA and the amplifier here? Okay, so the amplifier here is actually more likely to refer to a open operational amplifier. LNA here is the first stage of our transceiver. Actually receiver, the first stage of the receiver. Yeah. Its main role is to amplify rather small signal from the free space, like from the other antenna. Uh, the antenna transmit something, the signal, right? Uh, because the high loss of the free space, the signal amplitude before entering the LNA here is rather weak. So the LNA here is not operating like operational amplifier. It's more likely to act like a high frequency amplifier to boost the voltage swing of the rather small signal. Yeah. So what is the typical uh, swing input swing for this LNA? The power is smaller than minus 20 dB actually for a real scenario, or even worse if the signal is transmitted by the how to say the uh airspace, right? Airspace. Yeah. So actually the LNA is very highly sensitive circuit. Yeah, it must amplify the very big signal to a reasonable signal that can be used by other block. Okay. So the next one is the mixer. So what does it mean for mixer? Mixer actually means a circuit can convert frequency. Yeah. So uh convert frequency means the frequency can be increased or to be reduced, right? If the frequency is higher, convert to be higher, it refer to a up conversion. Instead, it will be a down conversion if the frequency is lower, right? So it actually acts as a conversion block. Okay, so the third one is PLL. This is also a very hot topic when you go into the industry. Yeah. Normally for PLL engineer, the minimum requirement is 5 years. Yeah. So undergraduate course is not sufficient to make sure you can enter the interview. Yeah, if you have interest in this field. So I think a master or PhD degree is helpful. Yeah. So PLL is what is a phase lock loop. Yeah. So what does uh when we use this PLL is actually a clock. Yeah, the PLL is actually a clock. Why we need a clock in our chip? So we have to synchronize the data by a clock, right? Before the data can be analyzed by the digital circuit. Yeah. So we need to have a very precisely robust clock to synchronize the incoming data. Yeah. So the specification for PLL is actually very hard to make very hard to ensure in many circumstances. So why is that? Because if we wish to synchronize a very high speed data, so the horizontal uh, movement of the clock must be limited to just tens of few femtosecond. AFS, yeah, femtosecond. Actually, this is very small. Femtosecond, very, very small. Yeah, 10 power minus 15, right? 10 power minus 15. This is very small amount. Yeah. So, which means that the PLL must generate a very clean clock to synchronize the high-speed data. Yeah. So what is the concept of high speed? So, high speed normally means the data rate higher than 100 gigabits per second. This is high speed. So what is the trend right now? The trend I think in United States already beyond maybe 800, right? Maybe 800 gigabit per second. So it's actually very high speed data rate. So the room allow for us to have noise on this PLL is rather small. So we have to design a PLL to have a very small, very, very small noise profile to ensure we can synchronize the data correctly. Yeah. So otherwise, we fail to synchronize data. The data will have increased, which is referred to the bit error rate, right? The BER of the system. So this is a very critical block. Yeah, that's why sometimes industry prefer a master PhD student because they have more chance or and more experience on designing this kind of circuit. Yeah. Okay, the next one is VCO. So what is that? It's a voltage control oscillator. So it's the core device in the PLL because the VCO generate the high frequency signal, which is used for synchronizing the data, right? It's actually the generation of the clock. Okay, so people will ask why we cannot just design a simple VCO. Yeah, we do not have to design PL, right? We just design VCO. So we just need a VCO to synchronize. So why we have to study? So PL, this is so difficult. Actually, the VCO is can generate high frequency data, but what is the frequency? Can you control it? It's hard to control it, right? Uh, VCO have in modern electronic device, VCO normally have very wide operating frequency. Yeah. Some talents VCO the operating frequency can vary from several gigabit, several gigahertz to tens of gigahertz. So it span a very wide frequency range of the source generation. So the PLL used to synchronize the VCO because we can use a rather low speed reference, which is a crystal reference, to synchronize the VCO and get a predefined output frequency. Yeah. So the VCO is not free running anymore in a PLL. Yeah. Without a PLL, the VCO is free running. We cannot actually control its output frequency. So we cannot synchronize any data rate. Yeah, with the PLL, we can synchronize the data rate as long as its output frequency can cover the input frequency. Okay. So so which means that we have to study source generation in VCO and also study how to control the VCO output frequency by PLL. And also we have to study how we can maintain the low noise of this specific circuit. Okay, radar and wireless connectivity are actually large system. Okay, so it cannot be done by a single person. It actually designed by a large group member. Anyway, but before interview in the industry, so we must gain some basic idea. So what is the limit of this circuit, and what is the trade-off between the performance for this circuit? Okay, the next one is power management. We have studied before, so it's about power conversion or voltage conversion. Yeah. Uh, Basically, we have the this in LDC is a LDO, right? It's a LDO and DC-DC converter, battery energy efficiency, reliability. So these are the main concern for this circuit. Yeah. So the next is a IC design and physical verification. And I think 10 years ago, people, 10 years ago, people can still work on this without a master degree, but right now I think it's somewhat difficult. The main reason is that the process right now is much more advanced than 10 years before. 10 years before, for some company, we still use the 180 micron, the CMOS technology, or I think even some company use the 65 nanometer, and the layout is somewhat easy to draw. So there are not too much rule for the IC layout. Yeah, I think all of you already know the DRC, DRC, which is a design rule check. Uh, uh, However, this situation become difficult right now because the technology now become too advanced for most of the undergraduate student. So right now in company, we have to design chips about using about below 16 nanometer maybe. Some company even using the 5 nanometer or below. So there are too many rules for us to understand right now. So it's already rather complicated for undergraduate student. Okay, so I think after this course, although this course does not cover the IC layout, but after this course, we still find a way to train ourselves with this IC layout. Yeah, it's hard to say they hire undergraduate student. Yeah, I cannot guarantee this, but this this ability is quite useful. Yeah, it's very useful. Sometimes we can gain some insight from when we draw the layout. Why? Because the layout sometimes reflect the circuit symmetry and the connectivity between different blocks. How I can say is that even though you have a very good performance in the pre-layout simulation, when you join a layout, you find difficulty in connecting them. Why? This because it's actually for integrated circuit is a 2D, right? It's a 2D topology. It's not for 3D. So the connectivity is sometimes difficult than you thought when you design in pre-simulation. So this will allow you to communicate with the design engineer to think if you have other way to uh, I mean to create another schematic so that you have more flexible in connectivity between different blocks. Yeah, this is more difficult in radio frequency design because the layout plastic is very critical. I think in during if you in the future you study the master or PhD course, when you draw the layout for high frequency, I mean uh, in radio frequency or millimeter wave, you will find the layout ultimately even truly will destroy the whole performance of your pre-layout simulation. Yeah, which means the layout is very critical. It's not something you think is just some labor, right? Some labor you don't have, you don't like to do, but it's actually very important. So it's very common that the layout engineer have to find a way to negotiate with the design engineer because there are so many trade-offs in the layout. Yeah. Okay, the next one is a test validation and application. So this is more likely to refer to the testing, right? The measurement. So after you have designed the circuit and verify them in the simulation and then tape out the circuit. In the next step, in the final step, you have to measure it. So this will test the ability of one's measurement and also how you can collect the data from the measurement. And for a beginner, so what is common is that your measurement result is quite different from your post layout simulation. Yeah, this is very common. Sometimes the measurement equipment or the environment can vary the result. Yeah, so you have to debug when this difference comes. So you must debug. So the difference come from the measurement setup or the measurement in accuracy, or you have made some mistake during the measurement. You have to find out. So this actually require you have a lot of experience on measuring different circuit. So I can share with you my experience during my PhD. During my first year, my tutor actually asked me to measure some circuit for my for the senior student. So why? One important issue is that the senior student do not have too much time for measurement. They are already close approaching the graduation. They need to focus on the paper writing, right? Paper writing or the defense of the PhD. So the tutor sometimes asks a first year student to measure for them. So during this study, we can actually study what's the response of the circuit. So why the measure results are quite different. Yeah. So normally we do not test just one circuit for one person. We test many circuit. Yeah. Some circuit have already been characterized, well verified. So we will measure it again to how to say to uh to regain the data from the measurement by comparing their paper, right? Their report. So from this way, we can study if the problem comes from my cell or from the chips. If the chip is not working, it's my problem. It's my problem, or is the chip just not working? So I must debug this. I must know the chip.